discuss some ideas. So firstly it was problem A. So let's see on the problem A and try to understand what the solution might be. So the first interesting thing here is that n is rather small, so maybe it can be use some masks, yeah? And translators contain some dp's and maybe some dp masks. So let's now understand what the solution. So there are some graph with n vertices, and what should we do with this graph? We should call the maximum sum of the capacities of all edges, and the capacity is minimum number of tokens of the endpoints. So you have some number of tokens, for example, like 5 tokens, and now you can give some vertices, some number of tokens, for example, like this 2 and 2, as example. So if you look at some edge, and the minimum number of tokens on some of the points is actually the capacity of this edge. And now we want to give some vertices, some number of points, so that the sum of all these points will equal to k, no, to s, yeah, to s, and s is not so big. Okay, so let's now understand how we can solve this problem. First, let's see on some answer. So if we look some answer, and can we obtain this answer? It's like some of the vertices will be with the 0 tokens, some of them will be with 1 token, with 2 tokens, and so on. So let's firstly give the all vertices some number of tokens, for example 0, and then we'll delete some tokens, and after that we'll give some other vertices only by 1 points, by 1 token, and we'll continue that process. So actually if we have some answer, it can be obtained like this. For some set of vertices, we'll give 0 points. Then we can delete some edges, or sorry, some vertices from this, and give all vertices in current set by plus 1 point. And each time we have 2 options. We can give all the vertices plus 1 token, and it will be this state, or this state. Or we can delete some vertices. So what we have now dp by mask, where mask is actually our current set of vertices, and the number of tokens that we can give to all these vertices. So let's do this operation. So we can delete some vertices. It's like there is not more than n variants to do this. Actually, it's the number of ones beating this mask. Yes, so you can delete something. And it will be dp mask without some hi, for example, and the same number of tokens. Or we can give to each vertex exactly 1 point, and it will be like dp mask and k minus number of points in that mask, like b and k, and is multiple count of masks, number of points in minus n. Okay, so now this is dp, and what it is now? You need to have the maximum sum of all capacities, So let's think about the capacity now. When we do this action, we just delete some edge, so the capacity now doesn't change. And when we do this thing, the capacity of all edges will be increased by 1. So the total capacity will be increased by the number of edges that contains in current mask. So it will have, for example, like something a mask is the number of edges in our current mask. Each edge will argue by 1 if we do this. Okay, so it will be like the maximum of this variant and this plus of mask. Okay, so in the tutorial we have the same explanation. Yeah, it's like here maximum possible sum, mask I and G tokens, and these two variants. So questions? So that was the dynamic by masks. Actually, maybe the dynamic is not a strong place. So it is very useful that we found it before the chapters. And it's really cool that some team passes task J. This task is for strings, so maybe the strings are in strong place and some dynamics, especially dynamics on graph, maybe not so strong. Okay, so let's see the next problem. The next problem was problem B about Snorri's map. It's also about dynamic. So what was the statement? You have some points with some weights on the plane. And you need to find some rectangular, and if you fix some rectangular, the cost of this rectangular will be the sum of costs of each point inside this rectangular. So this task is actually quite similar to some popular task. It's like popular task for the beginners. So let's see what is it. So you have an array of some elements, and you need to find the segment of the maximum sum. Then it's the first task on simple algorithms. So it's actually the same. Let's remind how to solve this task in 1D. So there are several solutions, and one of them is by linear time, which is too slow for our task now, and another one is by overtime recalculation, and then by logarithmic, actually recalculation by n multiplied by log, and then on the over 1 to find the answer. So what's the solution? If you have some segment tree, in each vertex of segment tree you contain 3 values. So the first value for some segment, so it's like this is some node in segment tree, it contains the maximum possible prefix of this segment, the maximum possible suffix of this segment, and the maximum possible segment inside this segment. So the same you have for the next segment or the next node. Yeah. And when you need to merge it and to have some also free these values for the parent of these two nodes, what you should do. So the maximum prefix now for all this segment, what is it? It's the maximum between the maximum prefix of the left and the sum of the whole plus the maximum of the left. It can become the brackets. Also the same for the suffix, is the maximum from the suffix of the right part plus the suffix of the left part plus the whole segment of the right. So actually you also need the sum. And so now we have this maximum prefix, maximum suffix, and how to update the maximum segment inside it. It's rather the maximum segment on the left side, on the right side, on this maximum suffix on the left side plus maximum prefix on the right side. So it's like in segment D, how can you solve the 1D problem. So let's do absolutely the same thing here. There was not a lot of points, about 2000, and let's sort them. And now we'll fix some horizontal line. After that, we will construct the segment tree. And now let's add all other points by these lines. So we will have these segments, we have these points sorted by the English coordinate. And so now we just add these points in this order. And when we add all points on some line, for example like this, we will ask in segment tree the maximum possible segment on that on the current array. So it's like after you add all these points, you have now the array for all these points, and now it doesn't matter in which English coordinate the points was, it's a one-dimensional problem now. And you just found the maximum segment in the segment tree. So the solution is sort this by and then we go through these endpoints and not more than endpoints, because you add only all other points in this sorting area. And each time after you add this point in your segment tree, you add some value to this x coordinate. It's by logarithm term. And after you construct the segment tree and adding each time this value, on the top of the segment tree will be the answer, the maximum segment. So it's n squared log. Okay, so questions? In tutorial there is just let's consider now the direction, and that is all. Okay, let's see on the next problem. The next problem was problem C. So for this problem you have some array also, and you need to understand the number of ways to choose some subsequence, so that each pair of your subsequence is at least x. Each pair is XOR of each pair is at least x. So and the numbers are in long type, and there are a lot of elements. How to solve this problem? We need to find the number of subsequence, so that each pair is like in E, XOR G, at least x. Let's firstly understand why this XOR is smaller as possible. We will consider these numbers in bits. So the number AE XOR AG is as less as possible when some prefix are equal, because if the prefixes are equal and there is some ones, so after XOR operation there will be zeros, and as much the prefix is more, as much the common prefix is bigger, then the XOR is smaller. So it seems that if we sort on numbers, only two consecutive numbers will have this the smallest sort. So that's the first observation. We need only to be afraid of some subsequent numbers. Okay, so after that, it seems that actually we don't need the subsequences. We actually have some set of numbers and just need to find some number of subsets in which this is okay. So now we have this bitwise tree, and let's have some kind of dynamic. So if we sort on all numbers, and we have some index I here, and for each I, we know the number of subsequents which are okay for us from this prefix. And now we want to have our number I to be in our subset. So we need to understand how many subsequences can also be continued by this element AI. So there is all such G's. So what is the last element can be? All such G's is okay if this inequality is true. So if you have this tree, how the tree looks like, you have some root and all these numbers with the first bit is the biggest bit, equals to 0 go to the left, all of the numbers with the one bit go to the right, and so on. And when we consider this number A with index I, let's see on the speeds of this number. This number AI, there's some bits. So if we have this bit equals to 1, we can only contain some numbers equals to 1 also here. So for example, let us see what will be. So we can, we should check, we should check, can we contain some numbers with the 0 bit here? Because we have this constraints for number x, and for example, x is looked also like some number in bitwise, and if there is some zeros, we need to understand the number of the number of numbers such that there is something and the suffix is at least this one. So it's like dynamic in our tree, and not so that such numbers here, but these numbers are actually the XOR with our element, because if we just XOR AI XOR AG, and this is AG, so this is should be at least X. So it's like X is like this. It's a standard dynamic. If we have some elements here equals to 1, then it doesn't matter what the list elements and the list bits are. And if we have these zeros, it's like we need to understand that it's okay here. So now let's go through our number AI, and if it has bit equals to 1, and in our XOR, for example, it's bit 0, then all numbers with bit 0 are okay for us. So we just add these numbers of numbers for our answer and go to the next bit. And if we have this situation that in our n its number, it's now it equals to 1, and in our XOR x it also we have bit equals to 1. So we need just to continue and don't add the other variable bits. And we have this bits equal to 0 and x has this bit, for example, also 0. Then all numbers with this bit equals to 1 are okay for us, and we just add the sum of these numbers and go to base bit 0. So each time when you do this some pass in the tree, you remove some number AI, and sometimes you add all the numbers of the other variable bits, and sometimes you don't add them. So it's like this, okay? Dynamic on the tree. So that's the summary of the solution. We need to sort these numbers and have some kind of DP, like DP is the number of ways to have this subsequence, and when we want to recalculate this DP, when we just add this number AA, we should add some numbers using our tree. So it's like n log time. Actually, where log is equals to 16 because it was told that our numbers are more than this, and there is also some kind of interesting things. You can see that 16 where it is, and it's because you can use some tree and it's 60 bits in each. Okay, so that was the solution. Dynamic on the tree. Okay. There is actually another short tutorial. Just calculate the TPD. So let's see on the next problem. Problem D. It was almost different. Actually, it was about just using the dynamic and control. So it's not real DP, but something like this. And so you need to find the number of such segments, so that the maximum of the segment minus the maximum of the segment minus its length is at least number k. Not at least, but not more than number k. So how to solve this problem? Let's use the dividing control. Divide the segment by 2 parts, and all the segments that are good for us are either on the left part, and we will count them when we go to the left, either on the right part, and we will count them when we go to the right, or they intersect our mirror. So how to calculate these numbers? We just, for example, can go by linear time to the left, and we will say that our maximum for some segment is on the left side. Then when you go to the left, you know the maximum, and also you can go to the right before this and found some information using step. For example, like the maximums. Okay? It's like here it's like some maximums. Maximum doesn't change, then another maximum. It doesn't change, another maximum. And when we fix the left border of the segment, you know the maximum. So you know that you can bring all elements that are less than maximum. Yeah, and because it's your maximum. And also by this equation, you can understand that the length should be at least k minus this maximum. So you can understand that there is some lower bound also, and you can finish your segment in each element here. So there is the number of ways for the right border of your segment. Yeah, so you fix the end segment, find these two, just for example 2 iterators, and multiply by sum here. So the number of these elements need to be added to your current answer, because the left border is fixed. And when you go to the left, what can be? So the maximum can only be greater. So this border will increase, and as the maximum becomes greater, lengths become also greater, by 1. So it's like the lengths maybe actually be only bigger, but you also can find this number by using the formula actually. So you can put the second iterator for it, just some index, and you can easily understand this numbers possible right borders. Okay, so each time you solve this by linear time, and then you divide this by the second parts from the left, like this, and go to the right and also divide by 2 parts. And there is a standard divide and control. So it will go by n log. Okay, questions? Okay, so let's go to the next problem, which is problem E, partition number. So what is problem about? You have some number n. No, you have some number m actually, and you need to have some numbers a1, a2, and so on plus ak, that their sum equals to m, and there is also some n numbers that are not allowed in your segments. This, and your ai shouldn't be equal to some of these numbers here. So some numbers was not allowed. Okay, so first we need to deal with this additional constraint of not using some numbers. We can do it, for example, like this. Let's understand how can we deal with it. If you have some sequence, and some of these numbers are equal to some a's, we'll just delete them and find the number of some sequence which is a smaller sum, and these elements can be any elements. And when we use odd number of such elements, we will use this minus such sequences, and using this even number, we will do plus these sequences. So it's like inclusion exclusion formula. Okay, so let's recalculate such things like even x is the number of ways to have the sum of equal to x using only these numbers. So it's like the number of ways to have this a e, some indexes e equals to x, and so e is not from set, not from some multiset, because you can use the same number twice there. From some multiset. Okay. And the number of these elements is even. Okay. It's even x. So the number of ways to have have the sum equals to x using some even number of elements from this array A. And the same thing is odd x. It's also the number of ways to have the same sum, but using odd number of elements. And now, how to calculate the answer to the problem. So let's fix this sum I. It will be maybe not I, for example x, and now we will have some elements which sum are x, and then from this forbidden array, for example, even x, and we'll multiply it by the number of ways to have sum equals to n minus x, where we can use any element. So mx is just the number of ways to get the sum x using any element. And the same thing with odd, but we need to delete them. Okay, so that's how can we manage with these additional constants. And now the problem is only how to calculate this p. So p by x is the number of ways to construct the sequence a1, a2, and so on. That how this sum equals to x. And there is also important thing that they are not decreasing order. If there was no such constraint, so the problem is easier. Yeah, just some general application, it's no problem. But how to manage with it? Well, firstly, it's like a classical problem. So we can use some standard degrees or some other things. I will show some solution. Okay. So let's have this polynomial 1 plus some z. Okay. Z plus z squared plus z cubed plus and so on. Then we will multiply it by this, z squared, z in false, and so on. It's like there is all this degrees. Then it will be like 3, and so on. So, and there is an infinity number of such polynomials. So, and let's see what is it actually. Yeah? It's also some polynomial, 1 plus a1 z1 plus a2 z2 and so on. And actually the coefficients of this polynomial will be this p by I. Let's see why. So how some coefficient before this appears. So it's something plus pi plus something. And how these coefficients before the a in its degree appears. So it's like I should be equal to some numbers of this. It's like some number from here, it will be e1 plus some number from here, which is 2 multiplied by e2. Some number from the next polynomial, some 3 multiplied by e3, and so on. And what is it actually? It's the number of ones, the number of twos, and the number of thirds in our representation of the number e. So if there was the same polynomial in each statement, it will be the normal coefficient without this additional constant. And now we have this number of ones, twos, and thirds, and so on. So this is like 1 plus 1, so on, and there is this number plus 2, and there is this number, and so on. Okay, so now we can present this number I using some number of numbers only by the one way. And what are these coefficients pi? So actually there is polynomial, and you actually don't need the infinity here because you summarize it, so it's the maximum degree will be equal to this m. Okay, and you know the FFT, so you can, for example, multiply these polynomials using FFT and have the answer. So it's one approach, and another approach. Sorry? Yeah, yes. It's like it is the beginning actually of the proving about some average theorem about pentagonal numbers. So it's in mention, but there is some formulas. So it looks like this. Let's see. Yeah. So this is our polynomial. Yeah. And actually maybe I can trust it. Oh, that's cool. And not actually cool. Okay. Let's see on this generating function. Okay. So this sequence is a geometric progression, so you could use this formula for this. Okay. And if you summarize all this, you will find this multiplication of these fractions, and now you can see the multiplication of these fractions, and the pentagonal theorem is like this. The multiplication of this is equal to some numbers in pentagonal numbers. And how can we use it? Yeah. So we can use it like this. So the Pn, it's actually what we need. It's the same as Pi here. Yeah. And we can calculate this Pn using the previous Pn and use only square numbers of the previous ones. So you can read more about these pentagonal numbers and pentagonal theorem, or you can use this FFT and multiplication of polynomials. Actually, this is some kind of classical problems. Okay, so that was problem E. It's about using some exclusion, inclusion, and after that we go to some classical problem. Okay, let's see on the next. It was problem F about some permutations. So what was asked in this problem? You need to know how many permutations so that E of P by E is equals to A. So it seems like each element I will go to some element, for example, it's here G, and Pg is equals to I. So there is only cycles of times 2. And we need to find the number of such permutations with additional constraints, that the number of inversions. It's when E is less than G, but AE is bigger than G. Okay? And the number of such pairs is equals to K. And there is one interesting fact that you don't need to know the numbers of this permutation. You actually only need to count the parity of these numbers. So if you read that something about parity is asked, so it's like maybe some permutations can be paired and there will be only even numbers, and some permutations can be paired, and actually it is. So let's see all these permutations. So firstly, with some permutation P, have some number of inverses equals to K. Let us see the inverse permutation of it. It will have the same number of inversions. Like when it's 1 and 1. It's here, for example, 3 and something and the inverse is for this 3 you have this 1. Okay. So these permutations have the same number of inversions. So they can be paired. And these permutations with only cycles of length equals to 2 actually can be paired. Because it's like when we see on the inverse permutation, it will be the same. So it can be paired because it is the same permutation. And now we see this. If we consider all permutations, each pair of the same inversions of K can be paired, and only these permutations that are needed to be counted is not paired. So if we will count the parity of all permutations with this number of inversions, the parity of these permutations will be the parity of those of them that are good for us. Okay. So, and how to calculate this? It's like some kind of DP. So let's construct permutation from 1, 2, and so on in increasing order. We have some numbers of permutations with inversions number of K, and so we now go through some elements from 1 to n, and we have some number of permutations with all numbers that are less than I. So you can choose any position so that you will add any number of additional inverses to it. And the constraints were rather small, it's only 500, so you can so you should optimize it more. It's like dp of the number of inversions at maximum n squared, so it's like 500 squared, and it's like the sum also some 500 variants, because for each number I, you can place it on some n places. Yeah, so it's like cubic solution in cubic type. Yeah, and if you want some formulas, it's like dpk, and we now fix some number I, and dpk equals to so we can add different numbers of inversions. If you have the previous dp, yeah, for the previous I, it's like you use only this I minus 1 numbers. Yeah, it's like you can choose some additional number of inversion G from 0. If you will add it to the last position to I minus 1, if you will add it to the first position, and if you pick the position G, or it's like the same as the position here at 0 inversion, the position here at I minus 1 inversion. So there is only one option how to add this number of inversions, and you just add this dp minus G. So from the previous, and yeah, it's like I and I minus 1. Okay. So questions? Okay, so the last problem for the first part of analyzing is problem G. It's about graph. Actually, it's about tree. You have some tree. And it was guaranteed that each vertex has the degree at most 5. And there was some density. Density is actually the mean, it's the mean of the weights of all vertices. And you need to find the number of some choosing subset L. Subset L is a subset of vertices. You can choose some number of vertices, for example. And as opposed to this subset is actually the maximum cost of some graph, actually of some connective subgraph. Yeah. So for example, there will be 3 graphs here, and in each graph you can find some subgraph also, and the cost of this subset will be the maximum cost of some subgraph, connective subgraph, and the cost of connective subgraph is 0. Yeah. So the mean number of all these weights. So how to solve this problem? Firstly, you can understand that if you have this maximum subgraph, you have also some subgraph which is star. So you actually need to understand only some values from this star subgraph. Why it is? Because if the graph is not a star, then it consists of 2 groups, minimum 2 groups. For example, here you can add all this into one graph, G1, and all other vertices, for example, here it will be, or G2. And when you add vertices, the mean can only be lower. Yeah? So there should be some this kind of star that has at least this mean. Okay, so there should be this star with this mean, and now we can do, for example, we can count using the masks each star. So there is n number of vertices, and 2 in this degree, a number of what each edge we will choose and which not. So we can put first choose all of these stars. Understand is the stars at least x, or at most x, yeah. And we can only choose these stars. And after that, we can write some dynamic on the subtrace, because for that star we can add some graph which will be in the subset A. So your star is the subset S, and it is a subset of some bigger set S, and the question was about the number of such set S. You can do it by dynamic of the subtrees. For example, like the number of such subtrees here, so the number of some stars, and it's like you can take this vertex and you cannot take this vertex, and the number of children, some of it, if you can this take this vertex, and actually that's it. Okay, so some kind of subtree dynamic. This constant find was for our masks of S, so that you could know a lot of them. Okay, so that work with the first 7 problems. So here is about 10 teams, 10 by 7, 70, and so I hope that there will be about 60 accepts during the solving. Okay, so let's solve now.
Studying the vertex for